All right, everyone. Today is Monday, the 23rd. We're getting ready to start our second week. Um, Please take note that it is very possible that you will receive either an email or a phone call or some kind of contact just to make sure that you are all staying on track and that your folks know what you're up to and how you're doing. I am hoping that most of you, when I check in to make sure that you're doing your work, that we'll find that there's no real reason other than just to say thank you, that you guys have been on track. And I appreciate those of you that consistently come to join me. I see Daniel and Caitlin, you guys are there, and I really do appreciate it. Hoping that everybody's still around and things are going well. What we're going to do today is, hey, Mr. Webb, hopefully you guys have had a good weekend. We're going to introduce some new material, and then if you have any questions on anything from your no reassignment or from what we did today, we'll go ahead and make sure that I answer all your questions before we sign off. I want to make sure that I give you a second to copy what we're looking at so that you can move with me and not kind of try to catch up. So one of the things that I have found is with this next theorem, it works best if we pay attention to the fact that we do have these parallel lines. So first off, you're going to see a picture that pretty clearly talks about a bunch of parallel lines. And the theorem says that parallel lines will divide our transversals proportionally. And again, remember, proportionally means that their ratios reduce to the same rate. So every time you see proportionally, that means ratios are equal. So noticing first that I have 1, 2, 3, 4 lines that are all parallel to each other. I can also see that I have 2 different transversals that I'm talking about in here. Couple things that you'll see is that we end up playing what's called the matching game. And what happens is we want to finish our proportion. So sometimes it's simply complete the proportion. And what we're doing is we're going to try to match everything at the same rate. So for instance, if I said AB over BC, you can see that right here I have a segment AB. And then I have another segment BC, and I'm talking about the lengths of those 2 segments. I want to be able to, on the other side, the other transversal, match the exact same ratio. So I know there's 10 of you right now watching. Can anybody tell me if on one side it's AB over BC, what would the other side look like? Very good. That's it. That's as hard as this gets. I see a couple of you guys did chime in. We have LM over MN. That's it. Thank you. Awesome. Oh, look at all of you. Not gonna lie, miss being with you guys in the classroom. It makes it a lot easier. Well done, guys. Thank you. So now let's try this one. If I said AD over CD, what's that going to make? And as I wait to fill that answer in, I see we've got some answers coming up. How about this one? If I said BC over MN, that's an ugly N, what would it be if I had to fill in CD? Perfect. Everybody's getting them right, so that's awesome. LP over NP is correct. So if I wanted, I'd end up with AD, so the full segment over just part of it. We would want the full segment over just the part of it. So then on this one, if we had BC to MN, I'd want CD, and there you go, NP. So notice how I had to kind of give us a little bit of a hint for the CD because you wouldn't have known that we were going to go side to side. So we had to make sure that we did end up matching the right segments. So there's NP. Nice job. So I could go on and on and on, and all it would be is making sure that we're matching the same pattern. So you are going to be asked as part of your final assessment of this chapter to kind of do the matching game. So in your notebooks right now, again, I'm going to suggest that because in my opinion, this matching game, this is a test question. And that you should put in your notebook that this is a test question so that you know to go back and kind of remember the matching game. I've also said the word matching game a bunch of times, so that might be something to remember here. So keep this example in mind that when it's just our parallel lines cut by two transversals, we're going to play the matching game. So why is this so important? We like shortcuts. Anywhere we can have shortcuts with anything, truly, we would prefer to do the shortcut because we figure it's faster. The problem is sometimes we end up making a wrong turn, we get caught up, we make mistakes. So we always have to be careful with shortcuts. So I am going to put a little bit of a note here that what we're working on is kind of like a shortcut, because we have to make sure that we remember what our rule says. So you're going to see in this example a picture that looks like some of the other stuff we just got done talking about. And I am going to put our parallel lines in. I'm going to get creative. A, B, C, D, and E. And I'm going to tell you that this guy right here is 9, and this guy is 3. I'm going to tell you that this one is 12, and I want us to figure out what that one is. And then I'm going to tell you that this one is 8, and I want to know how much that guy is. So, of course, the directions are just going to be solve for X and Y. And when you get a chance, I want you to tell me what you think X and Y are both going to be, because I think we can see that there's a pattern. So if you could tell me what you think X and Y are going to be, I want to know what your input is, because I guarantee you're going to be right in some instances and wrong in others. So I know that doesn't sound really promising. You don't want to be wrong. But I will say everyone's going to answer the same thing, so it's okay. Morgan, which one do you think 4 is, X or Y? All right, so let's just take a look because I'm looking at a lot of really good answers here. X, I think, is 4, and I see Y is 16. So I want us to make sure that what we're looking at is correct. So we want to look for these patterns. Now we have to remember, if we're going to use this shortcut, that it matches these parallel lines. So here's our parallel lines. And these are the transversals. So according to our rule at the top of playing the matching game, if we use our parallel line proportionality idea, we do end up with this idea that 9 to 3 should match 12 to X. And in some cases, we can see that we have 3 to 1, and this should be a 3 to 1. They should both reduce to the same ratio. And it works. You would know that X is going to be 4. And we're happy because we can do that mentally. Now, the problem is 8 and Y are not transversals. Our parallel lines, they're not being divided in any way, shape, or form. So when solving for your parallel lines, you can't use the shortcut. So when solving for the length of the parallel sides, no shortcut. We end up having to split our triangles again anyway. So this is where the shortcut kind of fails us because we're very quick to want to say what our answer should be. So what we're supposed to do then is we're actually supposed to split the triangles again and look at them as 2 separate triangles, where here's 9, 12, and 8. And here's another one. And again, who knows if my triangles are to scale or not. That's not an issue. It's more for visual effect anyway. But here's Y. And now I know 9 plus 3 is actually 12. So without using any of the values that I already found, because who knows, maybe I'm wrong. Maybe I did the math wrong for X. So I don't want to rely on my own work. I'm going to use the 9 and the 12. And I'm actually going to now use that to help solve for Y. So I end up with 9 over 12, left to right, 8 over Y, left to right. And when I cross multiply, I have 9Y equals 96. And when I divide by 9, we end up with 10 and 2/3. And so what I need to make sure of is that I'm looking at it doesn't match the same ratio because these aren't full triangles. These are just parts of our transversal. So it works well on one side. You cannot use the shortcut with the other one. So we end up with Y is 10 and 2/3, which is not what at least most of us, including myself, if I would have looked at this, would have immediately thought to answer. And I purposely wanted to make sure it was something that wasn't nice and neat. So let's go ahead and look at another example, one where I know people will get caught up with using the shortcut too quickly. And then maybe you'll notice that's why I said sometimes the shortcut isn't a good idea. So let's do this one real quick. Again, another picture that looks similar to what we've been looking at. And when you get a chance, tell me what you think A and B are going to be. You are correct. A is going to be 5. And it should be that fast because I'm paying attention to the parallel lines. These guys right here tell me that my transversals can be split proportionally. So the transversals were divided in a 2-to-1 relationship. So our shortcut tells me that the transversals now again, what ends, and that's something, and I will say, Morgan, without a doubt, 40 comes up so much. And I'm actually really happy that you said 40 because I want to ask, and you have no idea how often I see this. Do you notice that B is physically smaller than YZ? And it's physically shorter than YZ, but the fact that a value bigger than 20 shows up more often than not kind of just tells me that we're looking at this 2-to-1 relationship, but we're not paying attention to the structure of the actual triangle. And it happens all the time. So we have to pay attention first. Does it logically make sense? And then, yes, I'm going to agree, Beth, the next one that shows up the most is 10 because it fits this 2-to-1, 2-to-1. So why not this 2-to-1? And again, the issue is these are not transversals. So because B is not XV, which we have as B, is not part of a transversal. So it won't be divided proportionally because it's not split into pieces anyway. So we can't use the shortcut. So where before we were able to say that A is in fact 5, there is no doubt A fits that pattern and I can write down the answer and move on. I need to take a little bit more time, and again we are going to split our triangles so that we can visually see what our scale factor really is for the actual triangles, not just parts of the figure. And again, because I don't want to rely on my own work, I'm going to only use, again, what was given to me in the problem, and that is that this side is 21, and this side is 20. So when I look at the values that the problem gave me, it's those two. So when I set up my ratio, I know small to big or left to right. I'm going to set it up as 14 to 21. Should be the same as, again, small to big, left to right, B over 20. And when I cross multiply, we end up with 21B equals 280. And when we divide by 21, we end up with, and again, I have this fraction that thankfully it wasn't something that came out to be, again, a mental math thing. Some of us aren't going to see that that's the case. But if I plug that back in, we should have the exact same scale factor all the way. Can anybody tell me what the actual scale factor is? We did the work to find B, but what is the relationship of the small one to the bigger one? If I was asked for the actual scale factor, which I can only find if I have two figures. Over here, these are not full shapes. They're just segments that are within our shape. But what is the actual scale factor of small to big or left to right? Good. It should reduce to 2/3. You have 14 to 21. You would have 10 to 15. The scale factor is 2 to 3. So recognize we don't have a scale factor when we're using our theorem. It's just a shortcut. We do get a scale factor when we have two shapes to compare it to. So that's just the first part. It again is a shortcut. You're going to look to use the shortcut to just make things go a little faster. If all you really had to do, if you noticed things were parallel, was truly put some work in to find B because you could visually solve for A, why not go faster? You don't have to. You can always separate the triangles and do the work with your scale factor. Good job. I'm really happy to see how many of you put in the right scale factor. So then what we're looking at is what happens if our triangles have another situation. And this is now called our angle bisector. And our angle bisector similarity theorem, not really what it's probably called, and I don't even know if it has a name, but it occurs when an angle bisector shows up in a triangle. Again, it's a shortcut. It's a shortcut that works. It's one that I'm going to suggest because what you're looking at is going to be a triangle, and it's going to look very similar to something we did earlier this semester, but it's not going to have what would have looked like a quadrilateral. Earlier in some of our past work, we had something, I'm going to use a scratch piece of paper just to kind of show you. We had another angle bisector theorem where we put our bisector in and we saw that, and we said that here's a point on the angle bisector, and then all of a sudden we did this. And we said that they were equidistant. This point was equidistant. And this is where we talked about our angle bisector was called an orthocenter. But notice how this isn't a triangle. This guy right here is a four-sided figure. So what we looked at in our segments, our angle bisectors with our medians, altitudes, that chapter, this and this are going to be very different. This has four sides when we closed everything off. So we're not going to be talking about this situation. Notice I'm starting with a triangle, and then I'm going to put an angle bisector in here. So it goes straight across. And what this tells me when we write this part out is that if there's an angle bisector, so if an angle is bisected in a triangle, So if an angle is bisected in a triangle, then the bisector divides the opposite side proportionally with the sides of the angle. So what the heck does that say? Well, let's talk about the opposite side. Here's the angle. Here's the opposite side. So I have to know what the angle is that we're talking about. There's my opposite side. And then when we're talking about with the sides of the angle, that's these two guys. They're the ones that touch to make the angle. So we have our opposite side and we have the sides that make the angle. So if in this problem what we were looking at was the length of this side was E and the length of this side was F, and the length of this segment from there to the bisector was N, and the length from the bisector to the segment was P. Again, just giving it random variables. For it to divide it proportionally means it has to have the same ratio. That means that if I match this from E to F, notice one half of this picture, one side of this picture to the other, it would have to match the same thing at the bottom, one side to the other. So if E is to F, then it has to match with M to P. Now I could have said a variation of this which would do the exact same thing. What if I decided to go E to M? Again, playing the matching game, E to M. What would have to happen on the other side? Yep, it would have to be F to P. So we definitely want to make sure that we have the same match. And here's what we always have to be careful of. If you cross multiply, your E and P should still multiply together. Your F and M should still multiply together. The only thing you don't want to do not cross through the bisector when setting up your proportion. E over P would not work with M over F. So you don't want to make that X shape this way. Awesome. So again, this is something that we want to use so that we can get through it faster and we don't have to worry about taking a big triangle and a small triangle. So with this theorem, it makes it a lot faster. So let's just look at two examples. Again, we start with a triangle when we do this. The angle bisector may not be as obvious as that guy. He's a little obnoxious. And already it's possible that you know what the answer is. simply because you might see the pattern a lot faster. Anybody know what the answer is going to be right away? Yep. So we could, again, set up our proportion, and we could do x over 20 equals 12 over 24. Again, I want to keep the pattern the same, bottom to top, bottom to top. And I could just cross multiply and go ahead and solve. I could also reduce and see that this is x over 20 equals 1 over 2. So either way, it really doesn't matter, because when you divide, you can still get x is 10. So just depends on how much you want to save time with. So that's one way to go about doing this. Now, I could look at, let's see. And we could do this one. It's the same idea. There's not much different here. We just have to remember that when we are working this one out, recognize that you do have a quantity. So again, setting this up, 4 to 6, same pattern, x plus 2 over 10. So top to bottom, top to bottom. And when we cross multiply, we end up with 40 equals 6x plus 12. And when we subtract 12, you are going to end up with 28. And when you divide by 6, it's going to be a fraction again, but nothing wrong with fractions. We end up with 4 2/3, or 4 point, and then our repeating 6's. Yep, 4 2/3. Nice job, Beth. You beat me to it. And that truly is the hardest it gets. Nice job, Riley. Thank you, guys. So before we sign off for the day, I keep talking about, as long as we make sure our patterns stay the same, all of these are going to work out to be the same. So where Beth may have set it up one way, Riley may have said 4 over x plus 2 equals 6 over 10, and it'll still work out. So I do want to very quickly talk about, how could you check if you're asked, are they equivalent? Are they the same? So one of the things that we said was foolproof this entire time was cross-multiplying. No matter what, we should be able to figure everything out just by cross-multiplying. So the last thing that I want to talk about is equivalence. And we don't want to call them, are they equal? Because we got too many equal signs, because proportions have equal signs in them. But that's truly all we're talking about with the word equivalent. Equivalent is just seeing, are both situations, and in this case our proportions, equal? Do they mean the same thing? So that's what we want to check here. So the way the question is going to be phrased is it's going to simply say, if x over y is the same is equal to 2 over 3, then x over 2 is equal to y over 3. And the question is, are they equivalent? And that's all you're going to be asked, is if they are the same. So in our hypothesis here, is it going to match what's here? So you want to know that the hypothesis, and that goes back a couple chapters, so we want the hypothesis to match the conclusion. If they don't match, they're not equivalent. If they match, then they're equivalent. And the only way to do that is to cross multiply. Now, a lot of times you'll hear people say, just follow the pattern. If the pattern works, then it works. Sometimes that's not as easy to see. So cross multiply and check. If I take x times 3, I end up with 3x. Y times 2, that's going to be 2x. This is what we want. So then I'm going to do the same thing over here. 2 times, oops. Why didn't you tell me? 2 times y, and when I cross multiply in this direction, 3 times x. Now, I get that 2y's on one side and 3x is on the other side, but they are still equal. Because we could rewrite it by what property? What property says that we can move them on either side of the equal sign and they stay the same? We had a bunch of properties. We had reflexive, which I now have you guys picking up on real fast. We had transitive, we had substitution, we had symmetric. So what allows us to move things to either side of our equal sign? Reflexive, symmetric, substitution, or transitive. It is symmetric. Well done. That's pretty awesome right there. And that is by the symmetric property. We've done that since algebra when we switch things back and forth because it just feels better. It is the symmetric property where we can just flip-flop these guys on either side. Awesome. All right, last one. And this is where sometimes when we see patterns, we're happy with patterns. People are like, I get this, no problem. Others, not so much. So that's why I said cross multiply always works. So Again, what happens in the hypothesis, we want that to match the conclusion. So anybody want to tell me if you think they're equivalent just by looking at it really fast? All right, let's just take a look because I see we're not quite sure. We've got some no's, we've got a yes. So let's check. Instead of guessing, that's where the cross multiplication is going to come into play. So if I cross multiply, I can see that the b and the x are going to multiply together. So whether I put bx or xb, doesn't matter. It's commutative. And if I multiply here, I'm going to get y times a. So in this one, I'm going to cross multiply. And now I'm going to take b times x plus y. And it is a quantity, so I'm going to make sure that I put that in parentheses. And when I multiply here, I have y times a plus b. And I have that in parentheses. So now what I want to do is I'm going to distribute because nothing changed just because I have a whole bunch of variables. It's all going to be the same. I'm going to distribute to the x and to the y, and over here to the a and to the b. So we have bx plus by equals a times y and b times y. And I want you to take a close look. What happens on both sides of my equation? I have like terms. So I want to combine like terms. The by's are on both sides of the equation. So let's combine like terms. So we're going to combine like terms. Yep, there's a by on both sides. So when we combine like terms, they're going to cancel. And what we do end up with, even though it didn't look like it at the beginning, they are in fact equivalent. So without a doubt, patterns help, shortcuts help, but without a doubt, working it out will still tell us. So yeah, you would have to subtract to combine our like terms, but in the end, xb and bx are the same, ya and ay are the same, so we can say yes, they are equivalent. Now, I do show this because it is something that you're going to be asked, but a lot of it just comes down to one of you did a problem one way with your proportion, the other one did it a different way, got the same answer, and it's because they are equivalent proportions. Why can't you look at the second set and just divide by y and b and get... So I agree. Over here, why can't we divide by y and why can't we divide by b? Can anybody tell us? There is something in that that doesn't allow us to just divide. What's going to be in that that proportion that's going to cause us some issues? I'm going to bring in my scratch paper here. But here's the thing, it's not just that they're going to cancel and leave an x and an a. Because if that was the case, you're right. That kind of tells me it's not. But mathematically, we can't do that because when we reduce, and I know that we're thinking about our Algebra 1, this guy and this guy make that impossible. We are not allowed to reduce top to bottom if a plus or minus signs show up. So if our plus or minus signs show up, you can't cancel top to bottom. What you're thinking about, Beth, is if I had xy over y, or AB over B. Notice how there's no plus or minus sign. Without that plus or minus sign, this is all multiplication and division. Multiplication and division are inverse operations. Addition and division are not opposite operations. They're not inverse operations. Here you can cancel. Here you can cancel. Up here, you're not allowed. So again, addition and division are not inverse operations. Multiplication and division are. So that's why, and it happens. I had honors algebra 2 just recently. We're making the same mistakes, and it's because we move so fast, we see it, and we don't slow ourselves down to pay attention to those inverse operations. So you are correct, and without you chatting with me, that wouldn't have been something we would have talked about. So others would have made that error, especially if these questions were asked. So I do truly appreciate that. So what you're going to find is, again, the pattern I'm not changing. I'm not going to overwhelm you with a bunch of stuff. I've already heard you guys got lots to do. But I am going to be checking to see if your assignments are finished or at least being worked on. Some have not started. Others are finished. But you know as well as I do, we are still working, and we are going to make sure we do our work so that we don't fall behind. You know me, I am not about excuses. No matter what's put in front of us, we're going to keep working, and we're going to better ourselves every day. And I appreciate you all for checking in and working. But please, again, remember that if there's any issues, you are to email me. You are to take screenshots of your questions and email me, and I will be reaching out. You can tell your friends either via email or phone to make sure that we're all staying on track, because again, I am still grading. You are still responsible, and report cards will still occur. So please make sure that we are doing all that we can to better ourselves and to stay on track. If you have any questions, I'm going to hang on here for about 30 more seconds. Otherwise, we are finished for the day, and check Google Classroom for everything. We'll talk to you guys tomorrow.